Yes, we are live.
All
Very
right.
good. Yes.
I shared a slides link. I'll also share it in this chat. So everybody can open that if you like, but you can share the screen I'm showing. I'll have an exercise in mind that I think will be fun.
Thank you. So, by the way, a Tumblr, I have ordered a Tumblr. It should arrive this week.
Nice.
So I can get the card on YaRG.
All right. So, okay. Yeah, I thought it would be good to get a little systematic about thinking about the mechanical side of the design we're doing. So I'm calling this the Yakusor Tumbler. I don't know if we came up with a specific name for this thing that we're building, which is the Tumbler mod. But the idea is, since full-blown CAD and mechanical stress strain type design or mechanical analysis is pretty hard, trying to think of like a paper napkin version we could usefully do. So I made this quick schematic diagram. So all these are grouped Google drawing type sketches. So side view, front view, top view, and the red dot is center of gravity. So what I thought we could do is think about and brainstorm a bunch of different specs for this vehicle's mechanical or dynamic movement properties and try to sketch them and think about how to specify them. So I did a couple just to get us started, and then maybe we can each try to draw one. I made a bunch of templates. All right, so here's the first one. So obvious spec, what would be the maximum forward climb angle? So in this configuration, if it's climbing up with the small wheel in the back, so this is not in the balancing mode, so we can talk about balancing mode too. This is the configuration with an extra wheel attached and the balancing turned off. But in this case, since it's sort of leaning backwards in a sense, the center of gravity will be over the tripod base, so it's going to be more stable. So the angle it can climb will probably be higher. Whereas if it's going the other way with the tripod in front, you can see the center of gravity is moving back. So it'll be able to climb less. If it goes steeper, it might topple backwards, something like that. Oh, and this big rectangle, it's an abstraction. It's supposed to represent the 3 layers of boards with stuff in it. So this is not a detailed picture. It's just paper napkin level. So this is one spec, forward and backward climb angles. Here's another one. This is one my professor at Cornell really liked to do to the RoboSoccer team. So whenever students would bring design for a robot for him, his test was just drop it from a height. If it survives, then it makes the next round. So this is,
okay, I just have to ask. You drop it static or drop it while you're moving forward?
Static. I think the moving forward won't really make that much difference because the falling velocity will be so high, it'll dominate the stresses. So usually for the RoboSoccer team, their test used to be about like waist high, so maybe 3-4 feet. And they were built really sturdily. So if it can survive that shock, chances are it'll survive well in a game doing aggressive maneuvering. But in this case, this is the sort of test which if we use too much double-sided tape that Anuraj likes, it'll fail this test.
So is the drop to a cushioned floor or is it on a hard floor?
One is more
because the tumbler would definitely break into 2.
I would say for our initial test with the tumbler model, we should do carpeted flooring maybe. But yeah, I mean, a real rover that we wanted to put out in the Mojave Desert, I mean, it is a real scenario, right? It drives off a cliff. It should be able to handle at least a little bit of a fall off a rock, right? And onto a rocky surface. So these are some specs. I think I made one more.
Well, the max drop height also sounds like a proxy for resilience in general, more than an expectation of an actual thing that's going to happen.
Yeah. Well,
you
in rovers,
from a helicopter.
Yeah.
Airplane.
Well, it could be actual expectations, but it doesn't have to be.
Well, if you think about it, the Mars rovers were, in fact, the first ones were dropped from a height. So the latest ones had the retro rocket lander that gently lowered it. But the previous missions, one of them had that balloon ball tetrahedron thing that fell and bounced a bunch of times and then opened like petals of a flower, that would have quite a lot of like repeated falling shock. And I think others have like literally just dropped at a fairly decent velocity on the surface. Yeah, but yeah, I think it's a realistic benchmark metric. Like at least a little falling height, I think, is important. Let's see. Yeah, this is tip over angle is like, you're going sideways. This is going to be common in rough terrain, and yeah, you can tip over sideways. This one, this is actually not a very realistic drawing. So if you actually did the proportions right, I think the tumbler is actually quite high. It's higher than this, I think. So this is not realistically proportioned. And especially if we add another layer to hold, say, an RPI or something, or just keep increasing the height, this is going to become more and more unstable. Anyway, so these are the few examples I came up with. I made a bunch of template slides like this. Let me actually delete this one. Yeah, so if you look from slide 7 onwards, I made a bunch of like blank template slides. So let's try a collaborative exercise. So take one of these blank template slides, delete the 2 views that you don't need, and use the remaining view. You can sort of move it and rotate it and stuff to try and sketch out another spec that's useful to think about, and then maybe we can brainstorm. Can you guys try? Let me actually demonstrate what I mean. So I'll just tag this as the one I'm going to work on. Maybe I'll work on some constraint that applies to the top view. So I'll delete these 2. Delete. Oops, this one is not grouped. Sorry. You may have to group them. Oh, wait, it is grouped. I don't know what the hell happened. Let me just delete it. So if need be, delete it. And this should be, yeah, this is grouped correctly. Yeah, so for example, one thing I might try just to demonstrate an example of what I mean is, let's maybe use, if there's an arc, or, oh yeah, curve should do it. So this would be, for example, a spec of a minimum turning radius without running the motors in different directions, right? So that could be one spec. If you're only running the motors forward, this is the minimum turning radius. And this, for example, would constrain the minimum space it needs to turn around 180 degrees. So if it's caught in a canyon, then it either has to back out, but if the camera is facing forwards and it has to do a 180 to pull out, then it will need at least this much space to turn around. Okay, so that's a demonstration spec. Let me put in an arrow. And we can call this, so this is, all right, so is it clear what we're trying to do? All right, so take one of the remaining template slides and let's each make one more.
How are we dividing them up? Okay, we can see.
Yeah, just pick one of the slides, put your initials on it, and work on it.
So what are the constraints? Like, is it always the turning radius, or like how? I didn't understand.
No, I mean, do one. Like I showed you 4 different things you can.
Okay.
So just pick something you think is relevant to mechanical properties and try and like sketch out what you mean so we can talk about it. So I did several very obvious ones. So maybe there's non-obvious ones we can think about. Anuraj's sketch has a morphing tumbler. Something happened to it.
Well, it tumbled.
Truly made for tumbling.
All right, let's give it another minute or two, and then we can discuss our candidates.
Wait. One of these.
All right, everybody ready to talk, or does anybody need a minute or two more? All right, let's get started. So where were we? Yeah, I described this one already. I'll go last. Why don't we start with Mayor? Yeah, Mayor surface roughness. Yeah, you want to describe what's going on here?
Yeah, sure. I actually I did two of them. They're similar but not the same. Surface roughness means that you have those little boulders, and then your tumbler has to, one wheel goes over a boulder, the other wheels don't. So it's a kind of complex type of tilting, and it's also very momentary.
And
I'm
are
not
those
sure.
pebbles kind of like slippery? Like, is it?
I didn't think of that.
Okay, I think there's
Maybe, I don't know.
I think there's two cases here. One is there is roughness as modeled by your pebbles, but they're kind of like stuck in place. But the other is like loose gravel, where your wheel is going to spin, right? So they require two different benchmarks.
Oh, that's something completely different.
Yeah.
When you just talk about level loose gravel, then you have issues of friction and how much you weigh it. But a different thing that's related to surface roughness is step size. You get to a step. How high a step? A straight step, not a asymmetric or whatever. Are you able to negotiate?
This one also, I think, has two separate cases because it's an asymmetric vehicle with a third wheel in the back that's smaller. If it hits with the big front wheel, it can take a bigger step.
Oh, I thought it was hit with a small wheel.
Yeah. So if
No, let me fix it.
Yeah, both are separate cases. It should be able to like navigate some level of step with both. Yeah, this is okay. Yeah, this is the other one. Yeah. Oh, you didn't delete the other one, I hope, because both are.
No. I just did flip the direction. I was writing as if it was a step with a small wheel was in front, but you're right, the big wheel is in front.
Yeah, but I'm saying that
what I meant.
both are cases,
What I
right?
meant.
Yeah, you should be able to do both. So there'll be two steps. Like if you're small wheel front, it should be able to navigate a small step. If it's big wheel in front, it can handle a somewhat bigger step. So there'll be two cases here: step size forward, step size backwards. And let's see who's next. Okay, Anuraj, you want to try explaining this? I can't interpret this diagram.
You're muted.
Anuraj, you're muted. We can't hear you.
Okay. So I was just thinking, once you have dropped it from a height, and if it topples, how do you come back up? So basically, different kinds of passive or active mechanism. So one obvious thing is you sort of have some sort of actuator on the top or on the sides that kind of creates some motion to make it upright. I think there is this hopping robot from JAXA. It was sent to some asteroid, right? It had some arm, and then it would flip, and then it would just flip here or jump here and there with that arm. So something like that. Or
BattleBots
like
also has a lot of examples.
yes, but you need like really powerful motors for it, I would say.
Yeah.
I don't know.
Uh,
And then
the- yeah.
the second option was just to have some sort of extra support on the other side, passive support. But that only helps in toppling in one direction, not the complete upright or the inverted position. And then like the last option is basically changing the shape of the robot so that it just naturally rolls to some inclination. Yeah, those were some.
Okay, yeah. I think you took the exercise in a redesign direction rather than a benchmarking direction. So I was trying to get at like how can we benchmark the existing design?
Okay,
We can
yeah.
do this exercise as well. Right, let's see, where are we next? Move this forward. All right, Rhett, yeah, what are we doing here?
Yeah, I drew this and then I started thinking about all the different things that sort of applied to. But this is kind of related to Myers as well, where like you kind of want to know how big of a how deep into something can this go before not being able to move forward. And maybe that's just maybe even just clearance is an important thing. Like if you were running over an object and you don't want to bottom out on it, that's a measure of this. But then I originally I was like trying to capture, oh, you're in like some deep sand or muck of some kind, and you want to be able to move forward.
This is
Yeah,
not
deep.
clearance. Clearance is distinct. Clearance is the largest obstacle you can just go over while being kind of like in the same regime. Here, because your wheels are immersed in some other material, the whole friction profile is going to change and stuff, right? So yes, this is not clearance.
Yeah, well, I think maybe I was thinking originally of clearance, and then I kept going back and forth about what I was trying to measure here. I guess both are important.
Yeah, we should just separate the two cases. So clearance would be basically the height of the undercarriage, and this would be something like the maximum depth the main wheel can sink and still keep moving forward. So it's kind of like, yeah, how much it can
Yeah,
get
I
submerged.
think the complicated part for that, like I started thinking about like sand, and like, well, I guess you've got to deal with the like how the wheel shape, like how deep you actually sink,
Yep.
or like the wheel shape impacts that, right? Whether you may not actually sink into the material at all, depending on the material. So from a benchmarking perspective, I don't know how to even capture that.
So I think there's two constraints which may be more or less active, depending on how sealed it is against sand or water or something. It may be limited by the power of the motor versus the leak proofness of the whole chassis, right? Like if it's
Yeah.
going in water, and the motor is not actually waterproofed, it can. Let me try and draw here what I mean here. Let's take a circle. The motor is kind of circular, right? So let's say this inner circle is the motor. The water can't touch the motor, which means the water line has to be just below the motor line, right? But if the motor is somewhat waterproof or sandproof, then you can go deeper. But then you have to ask how deep can you go, and then actually the resistance is too much for the power of the motor.
Yeah.
Yeah, this is a
Are you
complex.
sure the question is more resistance or more other things like slipping or like the wheel applying force in the wrong direction simultaneously?
Yeah. So it's if you do a spectrum from like this loose gravel case we talked about all the way to water, and there's like non-Newtonian
Mhm.
fluids in the middle and things like that. Yeah, this is a material science benchmark. You would have to like have classes of material fluids, Newtonian fluids, non-Newtonian fluids. Loose gravel is kind of like a shearing layers material environment. So you would classify this as like almost a taxonomy of 5 or 6 different material surfaces. Yeah, this is a
Okay,
good.
so there's this Chuck Norris movie from the '80s called Lone Wolf McQuade, And in the climax of this movie, they take him and his Texas Ranger Bronco or whatever it is. And they bury it in a big hole. They bury the whole thing in there. And he wakes up, he turns on his motor, and he shoots up out of the dirt because this powerful, powerful vehicle. That's what I want to capture. How deep can you bury the rover and have it shoot out?
Oh, so it's not material depth up to wheel height. It's above head height.
Hey,
Yeah.
well, now I'm thinking you can go all the way. Yeah.
Okay,
It's
so
a tunneling vehicle then, right? Then it becomes a tunneling vehicle, effectively.
well, it has loose material. Tell me, if you bury the rover with only its leader sticking out, can it defend itself against scavenger bots coming to steal parts?
Buried bot. All right, let's talk about Eric's case.
Sure. So just we mentioned that tumbler is pretty high, okay, and so I don't remember. It looks like a cage, more like more than having flat sides. So perhaps there is not so much wind resistance. Still, since it's higher than larger, so it's more like a moving tower rather than a Roomba, basically. Huh? So perhaps we need to benchmark what the wind resistance is. And so a bunch of issues is that since it's self-balancing, so because it's higher and larger, okay, but since it's self-balancing, it's basically fighting against wind, okay, more than its logic is also fighting the wind. And even more when we are on slope. So there is another slide related to slope and the maximum slope we can go up or down. Okay, so I guess this also is a factor. Okay? That's basically it. One more point is that since also the tumbler is symmetric as far as I know, so a benchmark can also be limited to one lateral wind resistance, maybe not need to study both.
Yeah, it does have lateral symmetry. And I was just Googling what the max wind speed is. I know Mars has like extremely high wind speeds, but it's very thin atmosphere. But Mojave, I couldn't immediately find a good number, but 10 to 15 kilometers per hour seems possible. But the wind speed in a generic desert can go as high as like 100 kilometers per hour. So yeah, that would be definitely enough to blow the rover over or like completely throw off its self-balancing if it's in self-balancing mode. And of course, at some point, it'll become a question of sheer mass. Like the rover is simply not heavy enough to not be like pushed by the raw force of the wind. Let's see.
Is this a continuous wind or gusts?
Yeah, that's a good point too. Yeah, there is a maximum wind and also a continuous stream, right? To take into account.
I think gusting can be like 100, 200% higher than average wind speeds. But if you have phenomena like tornadoes and sandstorms, then you would have steady high force winds as well for a while. Oh yeah, and that would also create like this is suggesting another metric for me, which is sandstorms. I don't know. It's like the wind version of the ground gravel stuff, right? You have sand blowing at you, and if your chassis is not fully protected, it's going to get all into your electronics and screw everything up. So how much particulate matter movement can it handle, right? Like X milligrams per cubic foot per second or some measure like that, I think. All right, so you guys want to do one more round? If you have one more idea, let's try one more idea. We are like 10 or 2. I think if we spend 15 minutes on one more idea, then I thought we could finish up by trying and designing like what an ideal Mars testing, field testing site would look like with various obstacle courses and stuff. So I made some more template slides. So let's do one more round of cases. Yeah.
Sure.
Oh yeah, I forgot to before we go there, I forgot to do mine. Let me quickly mention mine. So initially, I thought the in-place wire turning is not actually a difficult case, because if it's rotating around like its own center of mass, what can go wrong? But because it's actually not symmetric in all directions, it actually is a non-trivial case, right? If the red dotted one is the 90-degree rotated configuration, and when that happens, the rear wheel in the solid case is going to swing around and hit a wall if it's there. And in the same way, the side wheel is now going to be up against something, right? So you actually need clearance in the front and the side that you're turning away from to actually do an in-place turn. So you need more space than the bounding box of the rover itself. Anyway, I just wanted to do that one. All right, let's do one more round.
Wow. Have to be mechanical. No. How do I show it? I need to do a few things. Color.
All right. Shall we start discussing?
Sure.
Yeah.
Let's start with Anurag.
Yeah, so I thought about the like, what if it gets stuck in a slippery surface, and like, what are the different solutions you could use to get out of that situation? So obvious solutions are software solutions. You do some sort of fast spinning, or do some sort of traction control. I don't know how much of that is possible. And then hardware solutions, like having like more grip on the tires, but like you cannot predict if you are stuck in a slippery solution. So I didn't have much solutions for it, but this could be one of the situations that rover finds it in.
Yeah, so for any given solution, I think the way you would qualify the slippery surface is the maximum coefficient or minimum coefficient of friction it can handle before it basically has stalled wheels, right? It does its best, but it stays stuck. So there's, I'm trying to, I think again, you're trying to solve problems rather than like benchmarking the performance limits, right? Because I think this might be a interesting difference between mechanical and software electronics type engineering. In mechanical, often design proceeds by saying, what is the limit beyond which I should not go? Therefore, you just hard code the limit as something you try not to go beyond at all, right? So if it says that don't go on a surface more slippery than this coefficient of friction, like maybe you can handle water on the surface but not oil, don't go if you think there's oil, you'll get stuck. So it's a very conservative, like constraint driven design philosophy, I think. But yeah, this is an important one. So we should definitely put in a. Have you guys ever seen a proving track for a car factory? They're really fun to watch.
No.
Yeah, I've seen the ones in Detroit for Ford and stuff, and I've seen one for trucks in India for Tata. So there are these big, like Olympic stadium-like spaces with basically military-style obstacle courses of different types that test many of these. It's like benchmarking a chip or software, but with a whole bunch of like test conditions for mechanical properties. That was going to be my last suggested exercise, but let's go through people's remaining ideas here. I'll quickly do mine. I did a couple of obvious ones. There's a ceiling clearance. If you have like, an articulated arm or something else that moves, that's going to set the ceiling clearance height. And obviously there's going to be a stopping distance functions in the forward and backward directions. The faster you're moving, the longer it'll take to get a stop. So one way to not hit an obstacle is to stop before you hit it. So you keep track of stopping distance functions. All right. So this is a ret. Yeah.
Yeah, kind of related to previous ones, but I was thinking about what happens if you only do it to a single wheel, and the three-wheel geometry is a little bit difficult to represent in this diagram, but I think I get the idea.
Yeah, I think a three-wheeler will go through a discontinuous arc where the third wheel kind of lifts off and then suddenly comes back down or something. So it'll actually be an interesting obstacle avoidance step. This is, I think, is there a distinction between this case and the one Mayer drew earlier over here? Is this the same one? No, this is surface roughness. It's like, this is more like asymmetrically, like one wheel is running on sand and the other wheel is running on asphalt. Can you actually handle that situation? Like if you're going along the edge of an asphalt road and your two wheels are on different surfaces, that's this case. Whereas this one, I think, is a single obstacle. How high can you handle?
Yeah, like how high can a single wheel be raised without losing it?
They are similar.
Yes,
They are similar. Venkatesh, in order to show what you said, I would have shown it from the side with two surfaces of different colors.
Yeah. I'm going by a phrase surface roughness rather than the diagram, because surface roughness to me indicates like a continuous surface with certain roughness properties. You would measure the roughness and friction and stuff. All right, let's see. What else do we have? Okay, this was right. All right, this is Eric. Yeah.
Yep. So just thinking about crush resistance, okay, and so it can be related to carrying, which can be something interesting. And so Well, it's a bit of a crash test in a way, okay, to see how much the rover can take from downward pressure, right? Okay, and so I'm not sure it's relevant, but I was thinking that since it's a self-balancing rover, okay, I wonder whether it's not interesting to have a benchmark on pressure that is on the gravity center, above the gravity center, okay, which is usually on the axle, of the self-balancing wheels. Okay, so there is more resistance here, and at the extremities of the rover. Okay, because here we should expect to have to be able to fight less pressure. Okay, because the motors has also to fight against it, right? Okay. I don't have a physical tumbler yet, so I don't remember the small wheel at the behind. I thought it was completely self-balancing. Okay, but this also can be interesting because perhaps any load is likely to go there. Okay, or like a small carriage, basically. Right?
That wheel doesn't exist, so that was so like in the first version, like the plugin I made, there was no encoder signals coming to the ESP32, so basically it couldn't know the wheel position, so like so there was no self-balancing possible, and then it was kind of dragging with that support on. So what Venkat and I did was just glue caster wheel to that extra support it comes with. That is how it became a 3-wheel robot.
Okay.
So this is. Can you guys see my screen? If you stop sharing, you can see it.
Yeah.
So
Wait.
You added one.
yeah,
Okay.
so this is an added one. This is not a great one. This should be replaced by. Actually, Rek, were you the one who had the spherical ball-like third wheel on your original two-wheeler? Was that you?
That sounds, yeah, I think it was, yeah.
This
Yeah.
one, the problem is if the wheel, it's a regular caster, so it's going to swivel uncontrollably if you try to move in different directions. So what you want is an omnidirectional wheel that doesn't like slew randomly when you do that. But I have a feeling like even if we do solve self-balancing, if we want to use the tumbler as a rover test bed, we really should have two modes, and we should have the third wheel anyway. So we should have like self-balancing capability when the surface is relatively uniform. So we'll need to balance that, by the way. Right now, the wheel throws it off balance. I don't think the self-balancing algorithm will work because I don't think it can handle asymmetric things without redesign. So we'll need to add some counterweight to make it like balanced at the center of gravity. And then we should have two modes on the tumbler, which is self-balancing, which you can use for relatively smooth surfaces and where you can run around fast. But if it's like rough rowing terrain, you should switch to three-wheeled mode and do the tripod motion. So it should have two modes, I think. But yeah.
Okay,
So
I just want to remind you that being a third wheel is not a positive expression.
So it would be the third wheel when only two wheels are needed, right?
But like, yeah, it will also tilt the tumbler, right? So if you have some camera facing at a particular direction which is fixed, so basically it changes the direction of where it sees.
Oh yeah,
If you have two modes.
that's fixable. So one of the small projects I had was basically redesign the wheel you put on and like find a larger wheel that makes it level again, or like offset it so that it becomes stable at a horizontal orientation. You don't want it like inclined. And yeah, we can design the camera.
Yeah. Then like how does it self-balance if it's like already touching the third wheel is already touching the ground?
It can be like a very light touch. It'll like just take the pressure off that wheel kind of balancing. Yeah, or we can actually actuate it and like retract it like landing gear or something. So there's a couple of different solutions there. Okay, so this is like static load, so pressure from the top like carrying a payload, or an asymmetric load that's being carried on this little thing. So by the way, Eric, when you assemble it, you'll see that this is the dragging tail. So the way the out of the box tumbler, it doesn't have a wheel, but it does have that like tail like thing. So normally it just rests on that side, and when you turn it on, it'll go vertical and start self-balancing. But it's very unstable in the other side. If you push it in the other direction, it'll fall over 90 degrees and it can't get up. It can only get up if it falls over backwards onto its tail. So it's somewhat weird design. I would have put a tail in both directions, maybe.
But it should be easy to print a similar support for the other direction.
Yeah, this will take some work to think through, like what all to add here. One of the things I was thinking about, I think, is to see if we can rearrange things so we don't have to increase the height further, because higher is less stable and so forth. So we should keep it to, right now it's a 3-tiered vehicle, 3 tiers. If we add an RPI, there should be room to put it right there. But okay, so this is static loading, and this is making me think also of dynamic loading. Like, cat swatting at it is a dynamic load. A rock dropping on it from the top somehow is a sudden impact load. So there's a whole class of benchmarking scenarios over here. Okay, let's see, what's the next one? Yeah, Meyer, jaw graspability. What do you mean by this?
Yeah, we talked about dropping it, but you also want to lift it up.
Yeah.
And there's 2 ways of lifting up. You can have, like a hook that hooks somewhere, or you can just grab it with jaws. So if you grab it with jaws, where's the rover graspable without being crushed?
Yeah.
You have to be able to apply enough force. I mean, it's more complicated. It has what the size of the jaws are and so on. So near the center of gravity, it's easier to do because you have less torque. But also near the edges, you might be thinner material. So I suggested something.
And it'll also be driven by constraints, like you don't want to grasp the battery, for example, because that can puncture and be dangerous. You don't want to grasp delicate electronics. If you've ever looked out of if you ever looked out of the window of a plane, you might have noticed there are markings on the wings and on the engine cowling, which are hoist points and things like that. So they think about this stuff. Where can you actually put loads or put in a hook and lift it and things like that? So yeah, we should add some stuff like this to the rover. That'll be kind of interesting. All right, what is this one? Holiness.
Well, I couldn't help myself. Holiness. What size hole can you dig yourself out of? No, but unlike Red, I'm not covered with gunk. I'm just in the hole.
Okay. All right. Were you the last one? I think so. All right. So that's done.
That's it.
All right. Let's see. We have 5 minutes left, so I thought we could do one other last brainstorm, which is if you wanted to design a rover garden in the form of like a proving ground, what elements would you put in it? So we can just brainstorm a list. Proving ground.
Just 1 second. When you talk about a proving ground, there's a difference between, I don't know what to call them, small tests and endurance tests. You know what I mean? Do you distinguish between the two, or both of them have to be in the proving grounds?
Usually they're done separately. So these individual cases we were brainstorming today, they're like unit tests in software. And when you do like end-to-end endurance testing, you're actually testing 2 things. One is fatigue, which is you drive it over the same course over and over and drive it to failure, basically. Like how much can it keep going over rough ground before the axle fails, something like that. And the other is kind of like multiple stressors at once, right? So these unit tests also can be woven together into a system integration test, right? Like, so for example, take this, the right wheel obstacle, right? So this is a single obstacle, but imagine like a zigzag obstacle course where it's like right obstacle, left obstacle, right obstacle, left obstacle. And this will stress it in a system integration kind of way, because it's going to like stress things that don't handle side-to-side jostling well, right? Because one obstacle is different from like that kind of thing. So when you design a proving ground, typically you're looking to do basically the equivalent of like end-to-end system integration testing. Fatigue testing is usually done differently. Like you might do isolated. So there's like actually 2 different axes, basically. There is like unit tests versus system tests for like finite time versions, and then there is like fatigue versions of each of those, right? Like you can have a complicated circuit and keep driving it 100 times, or you can have like a, off and on load that you cycle through, which is a single unit test, but you do it 1,000 times till it fails. So I'll get us started. You guys can also directly edit or start your own slide. But yeah, sand trap, rumbler, rough stretch, two wheels on different surfaces. Yeah.
In an incline, like a hill.
I don't know if 3D printability of this at home is like a property or not. Like you should be able to build it by yourself at home.
That would be that would be the design testing equivalent of this is a performance testing. That would be kind of like design testing. Does that make sense? So it's like there is this concept of design for manufacturability and things like that. So you're talking about design for manufacturability in a home printing environment, basically. Yeah, that's again distinct from what we're doing here. It's kind of interesting that you keep going towards design and solutions.
Yeah, I was thinking about it because like if you're doing like kind of silicon design or silicon bring up or some electronics design, so the everything comes to you after everything has been designed, and then you're asked to do, if something is wrong, then if it can be fixed in the software or with what you're doing.
Yeah.
So that's why like I always go in that direction, because generally the engineering problems that come to me are like, okay, this is like what we have designed, what can you solve with it?
I mean, that cycle is there in mechanical design as well, but it's much more expensive and longer, right? Like if in the proving ground you find out that your engine block develops cracks after like a 10,000 kilometers, you're kind of fucked. You have to go back to the drawing board and redesign the engine from scratch, which is like a very long redesign loop. There are some things that you can easily fix with software, but the kinds of things you're testing, typically you kind of have to go back and do the mechanical redesign, which tends to be harder. Like if you think about like expensive vehicle recalls, they're like full recalls. The car has to be sent back. Like what was the one on the Tesla Cybertruck recently? The accelerator foot pedal had like a cover that kept slipping off, and it slipped off and got trapped under the accelerator pedal, or something, or the brake pedal or something, and you couldn't stop it. So that was very dangerous, and there's no way to fix that in software. You have to like send it back to the factory, and they have to like basically fasten it better.
But this also affects like the overall design philosophy, right? Like if you're making cheap rovers that you could basically throw away, then you could have faster design cycles.
Yeah. Or on the other hand, you kind of do the kinds of designs you were talking about, which was build in stuff that allows it to survive more scenarios. Where was your reshaping thing? Those would be this one. Yeah, those would be harder to test because this is like a much more reconfigurable thing. So you'd have to basically treat each of your configurations as a completely different vehicle that you test, and then you would do like transition testing, right? Like if it's in like configuration 1 and configuration 2, can it get stuck in configuration 1? Can it always easily switch to configuration 2? So that sort of thing happens. Like aircraft, what happens if the landing gear gets stuck in the down position? They were actually talking about that in the Air India crash recently. It turned out that was not the case. Something else happened, but yeah, that can happen. But yeah, I think mechanical is the general philosophy is if you've received a prototype mechanical design and you're testing it, you basically push it to its limit and qualify the limits. You don't try to solve the limits or like improve the limits. It's like, yeah, this is as much load as you can handle. Don't put more load on it. A weightlifting gym section.
No, I'm assuming that's what it means when you have weights. The robot has to lift this, lift that. I mean, it's a proving ground and it's a robot, so it can do whatever it wants.
I was thinking about a competition we had in like grade school for building you build something out of straws or popsicle sticks or whatever, and then the teacher puts a garbage can on top of it and just starts like putting more and more stuff on it, and you see which one gets crushed first.
I remember in my junior year design course, so this was a junior year course where the whole thing was to design a particular thing. And the challenge for us was to design and build a prototype device that could lift a pencil 15 centimeters and then drop it. And the input had to be a rotating crank. So you had to turn a handle. And several faculty came and they were like testing our designs. And one of the professors, his idea of stress testing our design was he would like rotate the crank as fast as he could, like as hard and fast as he could. Half the designs, the crank handle broke off.
Well, that's what we didn't do. Crash resistance. What happened if you bang into a wall?
Yeah. And the way I would turn that into a benchmarking metric is how fast can you crash into it and still expect to survive with anything functioning, right? The drop height is kind of a vertical crash test. This particular rover, I don't think can go fast enough to really damage itself by bumping into things. It's faster than it. It's a slow rover, but it can get hit by a car, right? It's going on the road and a car hits it, or a faster rover hits it. A dog kicks it. A horse is going and steps on it. So,
but still, even if you don't think that it goes fast enough, then that's a pretty good benchmark that at full speed it should be able to withstand hitting a wall and be okay.
It can't kill itself.
Yeah.
And especially in the apartment level testing I've been doing, every freaking time I've turned this thing on, it has run into a wall or a chair or something like that. I don't have enough room to not have it run into things.
So you're saying it's been well tested already, okay?
So it's like a quick kill switch, right? Like how do you switch it off if there is nothing, but you keep on crashing into something and then to basically kill itself.
So this actually we haven't looked at that. It has no active brakes. So the equivalent of brakes for this vehicle is just turn off the motors. But I don't know if there's like any mechanism for electronically like torquing the motor in the opposite direction to.
I think there is. So
there
basically, if you So I think the motor driver there is a standby mode in basic like it has a high torque.
Yeah, it can do both backwards and forwards. But we need to look into things like that because that would be the braking equivalent. Yeah, this might actually be fun to set up if we can find some space. I don't know that any of us has space to set up a proving ground.
Well,
but
if the rover is really small,
it's not that small. I think this will need a proving ground of maybe 30 by 30 meters or something to be reasonable. But what we can do is design like a proving ground kit, like a wedge for a slope, cat litter box with some sand in it. I don't know. And put that in a box, and then we can take it to some gym or something where we can like lay out the obstacles and run it.
We could do the opposite. We could build a software function that gives a score to any parks that you choose and tells you how good is it of a proving ground. 9 out of 10 or whatever.
Are you benchmarking the proving ground?
That's what it sounds like.
Yeah. How much of the test? It's basically test suite coverage in software terms, right? You define the benchmark in terms of like a whole bunch of unit and integration tests, and then you say, all right, how much of this test coverage is happening in this proving ground, something like that. We can also think about like how much of this can you actually try to do in simulation? Because I think actually many of these can be tested in simulation, like many of the geometric properties, obstacle clearance, friction, you can kind of model many of those things. So one of the interesting things we could try is create a simplified model of the tumbler that has the right geometry and friction on the wheels and stuff, and see if we can create a simulated proving ground. That might be fun.
That's cheating. That's exactly avoiding and discovering. You know, I don't have a picture, but I want to show. They have a kids rehabilitation hospital around here, and they built in a kind of garden, and has in it steps and pebbles and inclines and slippery grass areas. Okay, and children being rehabilitated practice. Now, if they're older, it's in a wheelchair. If they're younger, they're crawling. Okay, so, and it's not 30 by 30 meters. Of course, it doesn't have all of these functions, but it is for little people, you know.
Yeah. Oh, some things, yeah, you can't get away without like physical proving and testing. But I think, yeah, I mean, they're even doing self-driving training in basically Grand Theft Auto type simulators now. You can do a fair amount of like machine learning training in simulated environments. But yeah, at some point, your models are not going to be rich enough to test in simulation. So you do have to like crash testing is actually a good example. Like crash testing is complex enough physics that the simulation is probably not going to cut it. You're probably going to have to crash a couple of things. Anyway, so hopefully that was interesting. I don't know if we'll take this anywhere, but at least informally, we should try to like ruggedize our tumbler design to meet some of these specs, especially the we can maybe like identify 3 or 4 of the most important ones. I think like step height, it can clear, clearance height, slope it can handle. Some of those are like kind of basic for a rover function, right? So we should think about that. But yeah.
And so actually, just I guess I missed the very beginning of this, but the goal is to find what the maximum value is, or to like pick a value and then make sure that it can clear that value, and then you're good.
Yeah, usually that's called the factor of safety. Like usually it's tested to far greater extremes than you set your operating limits at. So yeah, you will say that it can handle like I don't know, 1 ton of stress, but you'll never put more than like 200 kilograms of stress on it, right? Like if this is these videos, if you look at them, they're really impressive to watch. Like the most impressive one I've seen is Boeing's wing loading test rigging. So this is the fuselage, this is the wing. It's flexed up and down. So when it has like heavy wind loading with turbulence and stuff, it can literally flap like a bird. If you've been on a rough flight, you'll see it flutter a little bit. But in testing, it goes as high as like 35, 40 degrees each way. So there's a huge range, like 60, 70 degrees. And they actually test it to failure. It snaps off. Like in early design testing, they push it hard enough that the wing breaks. So yeah, the factor of safety is pretty extreme on most of these things. Yeah. And I've seen car testing for what you're calling roughness testing, Amir. Like one way they do that is they have these treadmill type rigs in car factories, which with a bunch of rollers that can be programmed to mimic any road surface. So the unevenness is like programmed as the treadmill. They really put it through like bone jarring rattling. Like imagine the roughest road you can ever drive on and then multiply that by 10. That's the level of like jarring testing that they do for a typical consumer car. So it can handle a lot.
Yeah. They have that in treadmills for, you know, people with Parkinson's to train them not to trip. So, but they don't shake him up, and they definitely don't rough them up.
And I think Yasha mentioned this on one of our earliest calls. For rovers that actually go to space, the limits are going to be far higher because the highest mechanical stresses are going to be during launch. Basically, it's going to pull like 8 or 9 Gs, and it's going to be extreme high vibration for that part and the landing phase. So it's going to be designed for like 20 minutes of its entire lifespan. So it might have a 10-year design lifespan, but the mechanical design is stress tested against the 20 most critical minutes that it'll be under the highest stress. So many mechanical design situations actually have that quality where the test environment is like 5% of the operating envelope or design duration.
But the configuration is different, right? While launching and then when it's like actually in work.
I think they pulled in and folded down the wheels or something like that. So it does a little bit, but the perseverance
It's
and
still shaking, while you're taking off.
yeah, it's not super robustly tied down. I think it is locked down to some extent, but yeah, it's basically the same configuration that rolls around on Mars. But yeah, that is possible. There are like more complicated geometries that can be folded into a much more robust, travel safe configuration or something. So that's a class of designs to consider. A design that kind of has like a turtle type of property, right? It pulls in and becomes compact and safe for like takeoff and landing. But once it's safely on the ground, it can pull out its wheels and do stuff. All right. That's it from me. Next week is you, right, Eric?
Yes. So on the mini app, and so it's about having the mini app run on some DigitalOcean instance. Okay. So that it's independent of what I have here. And the second point is to try to get the Paycaster part back to work. Okay.
Yeah, I'll
So-
create the access for you.
Thank you.
All right.
Okay. See you next week.
See you guys.